Unit 7, Lesson 5, Trig Identities Part 2. So we're just going to exploring the identity. We're going to look at a couple more, like kind of extension from yesterday. So yesterday we talked about Pythagorean identities, we talked about quotient identities, and we talked about reciprocal identities. Okay, and the reciprocal and quotients you kind of already knew. They're pretty much just what we know in terms of our ratios. The trig identities were a little bit new, but overall that's what we went over. So use the quotient identity to show that sine x equals tan cos x. So it says just show that they're equal. Well, we know that for example, sine x is just sine x, so that's my left side. You know, if we do the left side, right side thing. So sine x is just sine x. Okay, and then if you write tan x as sine x over cos x, you simply see that these cancel. And so then you get sine x equals sine x. So just showing that the cosines cancel the tan there. So the cosine on the side will cancel the one in the denominator. So tan cos x is equal to sine x. Okay, in this statement, is this statement true for all values of x? To investigate, sketch the graph. So what's happening here, and I'm going to kind of give you a spoiler alert here, is that the problem is remember how we did stuff earlier where we simplified things? When we simplified stuff, did we disregard the known permissibles that we simplified? So I'm saying is when we cancel stuff, was that still a non-permissible, or was it not anymore? It still was. Yeah, no, it still was. You have to account for stuff that you cancel as non-permissibles. So when I cancel cos x, because cos x being on bottom, I have a problem, right? Because can cos be 0? Yeah, cos can be 0, pi over 2, 3 pi over 2, right? So my point is that these graphs are still going to be different even though they're equivalent to the same thing. Okay? So what happens is you're going to have some holes you have to think about. So the statement true for all values of x. To investigate, sketch the graphs of sine x and then tan x cos x on the grids below using the window. So when you do sine of x, it's going to look like so. Okay, and you do that one, it's going to look exactly very similar. Okay, it appears the graphs are identical, that f of x and g of x for all values of x, the interval 0 to pi. However, this is not the case as shown below. And so I already kind of gave you the spoiler alert, was that because the over cosine has issues, because cosine could be 0, when you do part 1 for f of pi over 2, you get 1. So I'm just going to write this here. If you plug this into just sine, pi over 2 at sine is 1. Okay, you plug in for the second one, you get undefined. It says error on your calculator if you plug that in radians. Okay. Then again, for the first one, if you do 3 pi over 2, we're going to get -1 for sine. And you put this one, you're going to get undefined error. Okay. So essentially, there's holes there. And we have to be able to notice that. Okay. So the graph of g of x has points of discontinuity. So that makes back to the points we talked about. So there's open holes there. And the cool thing is we know where those are at. So like we know that pi over 2, we expected it to be at 1, because we know if our simplified. Just like when we had, let's just do something very simple. Some of you guys look like you're spinning here. So let's do, and then let's do x plus 3. Okay, so those cancel. So we have the line x plus 3 is what we're going to see, right? But remember, what we're going to see is we're going to have a hole at 2 right there, right? That's open. And we know where that's at by plugging in. If I plug in -2 to 3, it's going to be at 1. So this would be at 1, whatever, okay? So my graph's a little bit off. But the point is the hole will happen in the normal spot. The graph doesn't change. It's still a sine x graph. So if you go back up to here, or we're going to do it right down here. Okay, so you're going to have your same sine graph. I'm going to go ahead and just draw it as it was. So we go up. See, 1, 2, 3, 4, 5, 6. So it's going to be peaking at the third one, pi over 2. And then it's going to come down to pi. 1, 2, 3. It's going to peak at the third one and then come back. And then I know that here and here are holes. At the 3 pi over 2 and the pi over 2 spot. So the graphs are consistently the same. You just have holes at those values for the g of x, the tan x cos x. Okay, so it says the graph g of x has points discontinuity at pi over 2 and 3 pi over 2. Explain why. I'm just going to write it simply. Division by 0 occurs. curves have 2 R's? I'm not sure. Okay. I don't think so. I think it's 1. Okay, division by 0 occurs. That's why. Show the correct graph. We just did that. So we can say that sine x equals tan x cos x as identity with non-permissible values at cosine x of 0. So they are identical in the sense of what the graph looks like, but they are going to have non-permissible values that create points of discontinuity. Okay? So then it says the restrictions on the identity are x can't be pi over 2 plus n pi. So that means, do you guys understand that? Pi over 2, 3 pi over 2, the next one, the next one. This distance between these points of discontinuity is pi. Happens every pi, there's going to be a hole. So I'm at the top or the bottom of my unit circle idea, I'm going to have issues. Because top and bottom are 0 for cosine. Okay? All right. So the holes in the graph may not appear on the calculator in the trig functions. However, using the zoom trig, you should be able to find that for degree mode or for radian mode can help you see it, just like we did before to kind of see that the graph actually breaks. You won't see it generally at the first part, but if you do zoom trig, you can see it. All right, so what's it say here? Non-permissible values of the identity. So non-permissible values of identity are determined by finding the non-permissible values of each side of the identity. So in determining non-permissible values, there are 2 areas to focus on. All tangent, cotangent, secant, cosecant functions have non-permissible values. Let me say that again. All cotangent, tangent, secant, and cosecant have non-permissibles. Why? Because they have stuff on the bottom, right? Tangent's got cos on the bottom, cotangent's got sine on the bottom, secant's got cosine on the bottom, cosecant's got sine on the bottom. Okay, so they all have non-permissibles. Okay, and so they gave it to you simply. Tan x and secant both have cos x, so they have non-permissibles of cos being 0. That's one we just did. Pi over 2, 3 pi over 2. Cotangent and cosecant have sine on the bottom, so their non-permissible values are actually the 0, pi, and 2 pi. Okay, the spots where sine is 0. Okay. If the identity has a denominator, then any 0 of the denominator will be a non-permissible. We know that. Okay. The non-permissible values are sometimes called restrictions to the identity. In many of these examples, the restrictions are the solutions to sine of x equals 0 or cosine of x equals 0. Simply what makes those things on the bottom be 0. Okay. Recall sine of x is 0 when n pi. Cosine of x is 0 for pi over 2 n pi. Okay. All right. Let's kind of get to some stuff here. So hints to proving an identity. So begin with more complex side. So start with the stuff that's harder. So that's why I know the first one was very simple, but obviously tan cos is more difficult than sine. So we start with the tan cos. If possible, use the reciprocal quotient Pythagorean identities to simplify, like the sides until you get them to be equivalent. If necessary, change all trig ratios to sine or cosines. So sometimes it helps to change them, sometimes it doesn't. I will say in general, the cotangent tangents, I usually gravitate towards changing those to sine and cosine. So you get them like together. Look for factoring to prove the identity. If there's a sum or difference, we're going to get to sum or difference stuff later, of fractions, but combine them as a single fraction. So the point is like we did yesterday, that 1 plus sine x, we want to make that one thing instead of 2 terms. Okay, so try to get things isolated to one trig function. So let's look at this here. So consider the statement 1 over cos x minus cos x equals sine x tan x. So we're verifying the statement's true for pi over 3. So that means we simply can just plug in pi over 3. So we're going to prove that plugging in pi over 3 here is going to be equivalent values. So that's all we have to do. So left side would be 1 over cos pi over 3 minus cos pi over 3. So I'm just going to simplify that. What's cosine of pi over 3? 1/2. So 1 over 1/2 is 2, right? Are you guys okay with that? Well, I'll write it. Okay, 1 over 1/2. We'll just write it like that for now. Minus 1/2. 1 over 1/2 is 2. 2 minus 1/2 is 3/2. So we get 3/2 for the left side. Okay, sine tan x. So we got the sine tan. So that means we put sine pi over 3, tan pi over 3. So sine of pi over 3 is the root 3 over 2 times what's tangent at pi over 3? Right, it's going to be root 3 when you simplify, right? It's going to be root 3 over 2 over 1 half, and then 1 half and the 2 on the root 3 over 2 cancel. And then you can see what happens here. Root 3 times root 3 is 3, and you get 2, because it's root 3 over 1. Multiply across, 3 halves. So left side equals right side. Use graph calculator to show the statement is probably an identity. Okay, so what you can do is you can go, we'll do it together here. We can go y1, we're going to put 1 over cos x minus cos x. y2, sine x and tan x. So the graphs should be identical. Okay, the graphs should be identical. So let's go ahead and look at that. Does everybody have this if they need it? Okay, let's go ahead and put it in the calculator. All right, so I'll make sure my right mode's here, but I got 1 divided by cos x, bracket, minus cos x. Okay, we're going to go down, we're going to clear. We're going to do sine x, tan x. Okay, and let's make sure I'm in the right mode. I should be in radian mode. I am. My window is 0 to 2 pi. My scale is one of the pi's. We'll leave it like that. Okay, yeah, and then -2 to 2. All that looks good. Okay, all of my scales look good, so let's see how this looks here. Okay, interesting. So the point is, though, is you're seeing some breaks here. So why is there breaks? And here, let me show you something. It's hard to tell, I guess. You can't. Well, first off, it says they should be identical. So watch. If I turn this one off, yeah, because they're asymptotes. So I turn the first one off, okay? Now I'm going to go turn the second one off so you can see that they're identical. You can't see it when they drop right on top of each other. So if I turn it off, so I get the same thing. I'm just showing they are identical. The point was they are identical. You do see there's asymptotes. There's asymptotes because 1 over cos x, right? Cos x being 0 is a problem. Tangent is sine over cos. Cos x being a problem. And then you said it was pi over 6, right? So this is 1, 2, 3. Looks like the third one is an issue. Well, what's 3 pi over 6? Pi over 2. That's why that's a problem, because cosine 0 at pi over 2. Okay? So it's kind of all coming full circle here. So where we're at here, so just say for part B, they are identical. And now we're going to look at it in general in terms of the restrictions. So prove the statement is identical by using an algebraic approach. So we're going to just do it with just the sine and cosines. We're not using a value now. So this is a little bit more, I don't know if I want to say work, but okay. So remember, the first step is we want to get them to be one fraction, right? That's what we said in our steps. How can I get that to be one fraction? Right, I'm going to go 1 cos x here, and I'm going to go minus, I'm going to cos x top, cos x bottom, so the top's now squared, right? Right, and so we have, so check this out, 1 minus cos squared x over cos x. And Fo already said it, 1 minus cos squared x, that's an identity. That's the Pythagorean identity. That's sine squared x. And so look at this, though. I have sine squared x over cosine x. So if I slide a sine out, I now have what? Tan. So it's sine x tan x. Okay, so we just went all the way to it. They stopped here. They stopped here, and then they just wrote, because the sine tan x gets there as well, sine x times sine x cos x. So they get sine squared x over cos x. So that's what they did. But I mean, either way, it's fine if you go all the way or not. You proved that they are identical. with their identities. Okay? But we do have restrictions, and the restrictions are cos x can't be 0. That's the restriction for both of them. So that happens at pi over 2 plus pi n, okay, for n, e, I, for all integers. Pi over 2 plus pi is 3 pi over 2, plus pi is 5 pi over 2, which is back to the pi over 2 spot. Okay, any questions? Okay, we just got 3 more examples. Good? All right. Okay, so prove the identity of sine x cosine squared x plus sine cubed x. Okay, equals 1 over cosecant x, algebraically, and determine the non-permissible values. So it says algebraically, it means we're trying to break things out and simplify. When you first look at that, let me just ask you, when you first look at that, what are you kind of seeing that might be there? Yeah, factor, good, but also in terms of identity. What identity looks like it's going to come? Yeah, like when I look at this, I see I have a cos squared and a sine cubed. I'm really close to the cos squared sine squared. Cos squared sine squared is 1, right? So when I first look at that, it's in that, I'm kind of thinking Pythagorean identity. Okay? So, and you said factor perfect, because look, if I pull a sine x out, boom, it's now a sine squared. So, first thing we're going to do is, we're doing the left side here. We're going to pull a sine x out with factoring. That gives me cos squared x plus sine squared x. What's that? Correct. So this one came out, and then one of these came out, right? It's like an x and an x cubed, right? I took the x out, and the x cubed is now an x squared, because there's sine x in both pieces. So yeah, we did take it out, the first one. Okay? And so then this is 1. We like that, so that's nothing. So we have sine x. Well, 1 over cosecant x, I mean, that's kind of silly. That's 1 over sine x, which is just sine x. So we got it. However, let's see here. We still got to be careful that we don't want cosecant to be 0. Okay? So if we don't want cosecant to be 0, then sine being 0 is still a problem. Because we still have a cos in a denominator. Because what would happen is if you did that 1 over cosecant, we were saying, well, you'll flip it. Well, yeah, you would, but you're still going to get 0 on the bottom before you flip. So it's still a problem. Okay? So this right here, I just want you should be thinking, oh, sine's an issue. So that means in this case, it's just going to be the n pi, okay, just straight up n pi for NEI. The reason it's straight up is because it starts at 0. So it can be a 0, a 1, a 2, a 3, okay? So it just starts at 0. That's why we don't have to do a pi over 2 with that one. Okay. Is there any issues with, because cosecant is sine? Yeah, this is good. Okay, so we'll stop there with that one. Okay, and example 3. Got that sine A, tan A stuff. Okay, so prove it algebraically. So obviously, which side's more difficult? The left side. So we're going to do the left side. We're also going to do it in the sense that we're going to do the kind of top and the bottom. So I'm doing sine A plus sine A cosine A. I wrote tangent in terms of sine and cosine. Okay, the 1 plus cosines can stay on the bottom. And then I'm going to get this to be a fraction with the common denominator. So that's going to be sine A cosine A over cos A. Right, so that was just rewriting tangent, and now I'm doing common denominator. Okay, I'm going to have to go to the right here for some more room for the left side. We still have a bottom, so I haven't done anything with this yet. I'll bring that in a second. Which one? It's right here. This is the top. Yeah. Yeah, just like that. So I'm going to put that together as one fraction. Okay. When you get to there, what are you thinking you can do? Can't do it. Nope. Can't cancel cosine. One on the bottom is attached with a plus sign, right?
No, but like on the top fraction.
Still can't because you can only do it to one piece of it because the other piece doesn't have it. So you don't want to do that. What's that? Can't combine them. What did you say? Yeah, you take a sign out. Take a sign out on the top. Now, this is what you guys get good at. The reason that looks good to me, if I take a sign out, what am I going to be left with? +1. Helps us, right? So if I do that, I take sine A out. I get cos A +1 all over cos A all over 1 plus cos A. Now, we know that this is over 1 here, so this is going to go right there, which means it what? Cancels. So that means this guy is going to cancel with this guy. And you're left with sine A cosine A. We'll stop there for that left side. That's our left side. The right side would be very quick. Yeah, that was left side. Left side is the more difficult one. The right side is 1 over cos A sine A, which means it's really sine A cos A. It's the right side. So sine A over cos A, sine A over cos A. Okay, any questions on that before we go to non-permissibles? So non-permissible in this one's going to be sine and cosine are going to be a problem. Because sine's a problem right here, and cosine's a problem on these pieces. Okay, and we also can't have what? There's one other one. Go. -1 for cosine. So what we can't have is, let's do non-permissibles. Here's the 3 things we're looking at. We can't have cos A can't be 0. Sine A can't be 0. Cos A can't be -1. And that's all of them. So there's just 3. So again, we kind of know the answers to these, right? So this one's pi over 2 again. So this is the pi over 2 plus pi n for any I. The sine 0 is the pi n1 for any I. And then one's cosine -1. Not pi. It's cosine -1 right there. Yeah. So pi, and this is n plus 2. Oh, sorry. It's not pi n. It's pi plus 2 pi n any I. Now these ones are really like pretty much going to get the same values. So the sine covers the cosine non-permissibles, but so we don't have to write it. That's what I'm saying. So like you wrote these three, you need to see that this one covers this one. So these right here are the only two you really need for your answer, because the third one's covered in the sine. Okay. I'm just saying, like, if you saw an answer, you need to understand that if you don't see that third answer, it's because it's included. I mean, if you wrote that down, I don't think that'd be wrong. No. Okay. All right. So then it says show the non-permissible values in the graph. So the ones we just did, the non-permissible values. So when you do this graph, I'll just kind of quickly sketch this here. So we got asymptote, 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 and it goes like this. And up here, and then it's just what the picture looks like. Okay. So the issue is there's actually just spots we have to make the holes on. There's a hole, because this is going by pi over 2 here. We know there's a hole here and a hole here, because that's stuff we canceled. Okay, and then you can see the other non-permissibles to the asymptotes. But the stuff we cancel would be at the pi and negative pi. Cotangent's going to be the same. I'll draw it again. Okay, so this one's going to have holes at the same spots, just these, for cotangent. Will be the holes there. So the original, just so you know, this one has non-permissibles for cos A being 0. Okay, that comes from tangent, and it has cos A being negative 1. That comes from right here on the bottom. Cotangent has an issue with sine or cos can't be 0 because you have cos over sine on the bottom there. So either 0 gets a 0 on the bottom, you get 1 over 0. All right, we're going to prove one more identity and call it a day. Any questions on the graph? Okay, I'll let you guys sketch after a second. I'll pause. All right, so let's take a look here. Example 4. Obviously, the more difficult side's which one? Left side. So we're going to attack the left side first. Okay, so you have secant squared minus 1 over secant squared. Now, the interesting thing is, secant squared minus 1 looks familiar. A good idea, but actually it doesn't help you on this one. I thought different squared first time I saw it too. You could factor that the secant x plus 1, cx minus 1, but actually secant squared x minus 1 is an identity. It's one of the Pythagorean ones. Secant squared minus 1 is equal to tangent. So secant squared x minus 1 is equal to tangent. Okay? So that means we're doing left side here. So left side would be secant squared x over tangent squared x. So if I rewrite that, that would be 1 over cosine squared x sine squared x over cosine squared x. And you can kind of see it now, I think. Maybe not, but boom, boom. 1 over sine squared x equals cosecant squared x. Okay, and that's it.